Today's public lecture is about bridging the ancient and the cosmic, insight from the Ishango-born and universe. The intersection of ancient wisdom and cutting-edge cosmological theories unveils a profound narrative about humanity's journey in understanding the universe. This public lecture will explore two distinct yet interconnected perspectives: the Ishango-born, one of humanity's earliest mathematical artifacts, and modern cosmology, a frontier of mathematical reasoning. The aim of today's lecture is to inspire a recognition of mathematics as a universal tool connecting past and future explorations, and to encourage youth in particular to see science as a powerful avenue of shaping the future. This joint public lecture, held short after the International Pi Day, which is the International Day of Mathematics, usually celebrated on 14th of March, will highlight Pi's enduring significance as a symbol of mathematical ingenuity, connecting ancient discoveries with contemporary scientific advancements. George Kamanayo Genju, I hope I pronounce correctly, Jangu, is a Rwandan-Belgian filmmaker renowned for his films La Fille du Grand Monsieur and Kazungu le Métis. Born in 1947 in Rwanda to a Belgian father and a Rwandan mother, he studied in Brussels before working as a cameraman. He later founded a production company called Videocam, through which he produced and directed several documentaries. Professionally, George worked as a cameraman and filmmaker, contributing to various documentaries and films that took him around the world. Additionally, he played a pivotal role in raising global awareness of the Ishango-born, an ancient artifact from the Congo Basin. Through his efforts, the Ishango-born, recognized as one of the earliest known mathematical tools, was introduced to a broader audience, highlighting its historical and cultural significance to the world. Dear participants, join me in welcoming Mr. Kamanayo to take us through his presentation.
Mon nom est double, c'est-à-dire je porte le nom de Kamanayo, qui est un nom rwandais, et Jangu, qui est un nom français. Donc, je suis métis, comme vous le voyez. Je ne suis pas scientifique, mais j'aime la science, parce que mon métier de caméraman d'abord, et puis producteur, c'est les sciences aussi. Et c'est ce métier qui m'a fait comprendre beaucoup de choses dans la vie, parce que j'ai pu voyager beaucoup, comme on vous a dit, et que j'ai vu que, surtout, il y a beaucoup de choses que nous ne comprenons pas, et que moi, j'appelle magie, la magie. Donc, l'os d'Ishango, que j'aime beaucoup, c'est correct, il y a des mathématiques là-dessus, mais il y a la magie aussi. L'os d'Ishango est un objet magique, mais scientifique aussi. Je vais vous dire comment j'ai trouvé l'os d'Ishango et comment j'ai entendu parler ça pour la première fois. J'avais fait un film qui s'appelle Pièce d'identité, c'est pas moi seul qui a fait le film, j'ai été coproducteur, mais le film a été réalisé par un monsieur qui s'appelait Ngangura. Et le film gagne le prix du FESPACO en 1999. Et je suis à la radio belge, on m'interviewe. Et la première chose qu'on me demande, c'est sur mon nom. Mais Kamanayo, c'est un nom bizarre, hein? J'ai dit oui. Et d'où viens-tu alors? Et moi je dis, je viens du Rwanda. Le Rwanda? Oh, les génocides! C'était comme ça qu'on nous voyait à l'époque, tu comprends? Et finalement, je retourne à mon bureau, et quand je suis à mon bureau, il y a un monsieur qui me téléphone, qui me dit, je viens d'écouter votre interview à la radio, il faut plutôt faire un film sur l'os du Shango. Moi, je ne savais pas ce que ça voulait dire, l'os du Shango. Et il me dit, écoute, je viendrai chez vous, je vais vous expliquer. Et le monsieur, il vient chez moi et il me dit que l'os du Shango, attends, je dois faire comme ça. Ah ben ça, c'est les endroits où j'ai été, tu vois. Ici, c'est un reportage que j'ai voulu faire sur Diana Fossey, chez les gorilles, à l'époque. Ici, c'était en Chine, si je ne me trompe pas, au Japon. Et ce monsieur, ce n'est pas un missionnaire, hein, c'est un mathématicien. Oui, je vous jure. Et ici, c'était au Soudan. Au Soudan, on cherchait dans un lac les origines de la désertification. Il y a un lac là-bas au Soudan, dans le désert, et quand on fait des forages, on peut trouver quand la désertification a commencé en réalité. Ça, c'est le film en question qui a gagné donc le FESPACO. Ça, c'est le roi du Massissi qui allait visiter en Belgique sa fille qui faisait des études, mais la fille ne faisait pas des études, elle était dans des bars. Et il est venu avec tous ses couronnes, tout ce qu'il portait, et à l'aéroport de Bruxelles, il a dû payer de la TVA pour ces objets-là. Et ici, maintenant, ça, c'est l'os de Shango qui est à l'intérieur. Et ici, j'ai fait des vols paraboliques. Des vols paraboliques, c'est l'avion, un Airbus, by the way, il monte au maximum qu'il peut aller, et puis il tombe. Il tombe, et quand tu es dedans, tu tombes avec l'avion, et c'est comme si tu tombes dans un tuyau. Par rapport à l'avion, ton poids est zéro. Donc tu flottes, tu voles comme un oiseau dans l'avion. Hein? Il faut faire attention parce que l'avion doit remonter de nouveau. Alors, quand tu te trouves tout à fait en haut, tu tombes 3 fois ton poids par terre. Mais ce sont des avions spéciaux. Eh ben, je le faisais pourquoi? Je le faisais parce que ce monsieur derrière moi, il s'appelle Vladimir Pletser. C'est un astronaute et c'est lui le patron aussi des vols paraboliques. Mais maintenant, j'ai sauté beaucoup de choses. Je reviens. Alors, il me dit, le professeur en question, qui s'appelle Dirk Höllebroek, qui était professeur à l'université de Louvain, et qui connaissait l'existence de cet objet qui était caché. Parce que les Belges, quand ils ont découvert ce qui était sur cet objet-là, notamment l'âge d'objet qui était de 22 000 ans, avec des nombres premiers en dessous de 20, avec une soustraction, une multiplication par 2, mais surtout la base de 12. Et quand ils ont vu ça, ils ont dit ça ne correspond pas avec les idées coloniales que nous avons, on le cache. Ils ont caché l'objet à peu près 30-40 ans. Alors, quand le professeur m'a dit ça, j'ai dit, est-ce que tu peux me montrer l'objet? Et il me dit, ah, ça vient trop tôt. Je vais vous dire pourquoi j'aime Shakespeare. Shakespeare, il mélange toujours la réalité avec un rêve. C'est le magie avec la réalité. C'est pour ça que j'aime Shakespeare. Et c'est quand tu fais un film, je suis filmmaker, quand tu fais un film, il faut un moment de rêve, mais il faut un moment de réalité pour que l'homme se reconnaisse dans le film. Voilà. Et c'est ça, l'ange d'Ishango. Ici, il est marqué 20 000 ans, mais en réalité, c'est 22 000 ans. Et les premières datations étaient même plus. Pourquoi? Parce qu'on l'a trouvé dans un endroit volcanique à Ishango. Et c'est grâce aussi au fait que c'est un endroit volcanique que l'objet est resté si intact si longtemps. Mais l'objet, vous le voyez comme ça, mais en réalité, c'est comme une pierre. Tu vois? Alors, les coches qui sont là-dessus, tu vois, ils sont enjancés. Tu vois? Ça correspond à ça. Ça correspond à ça. Et ça correspond à ça. Donc, vous voyez, il y a une manière de raisonnement là-dessus. Ce n'est pas, je vois une vache, je fais un trait, et je vois encore une vache, je fais encore un trait. Non, non, c'est beaucoup plus que ça, comme vous voyez. Alors, au bout, il y a un quartz. Il y a un quartz. On dirait que ce quartz servait peut-être à faire un dessin ou quelque chose. Nous ne savons pas. Mais quand les Belges ont trouvé tout ça là-dessus, ils ont dit, on ne va pas le montrer au public. On va le cacher. Jusque ce professeur Hulbrook me le dit, et il me dit, écoute, on doit aller au musée des sciences naturelles à Bruxelles, que vous connaissez, M. Turok, et l'objet était au 19e étage dans un petit tiroir. Alors, toi aussi, tu l'as vu, hein, n'est-ce pas? Alors, on a ouvert le petit tiroir, et c'est la première fois que j'ai vu cet objet. J'ai une copie avec moi. Ça, c'est la copie en bronze, copie conforme, en bronze. Hein? Tantôt, les enfants, vous pouvez le toucher. Et c'est une copie en bronze. Alors, quand j'ai vu ça pour la première fois, il y avait quelque chose de magique en moi. J'avais peur. J'avais peur et j'étais quand même curieux de le voir. Je l'ai approché, on m'a montré, mais peut-être que c'est mon côté africain, je ne sais pas. C'était comme... je ne sais pas, c'est comme je faisais un péché ou un truc comme ça, hein, de voir un truc qu'on a caché pendant 40 ans. Déjà, je ne comprenais pas pourquoi on avait caché. Et puis, j'ai fait quelques photos et je demande aux gens qui étaient là, j'ai dit, est-ce que je peux revenir avec une équipe de tournage? Parce qu'à cette époque, je produisais une émission sur TV5 Monde et cette émission était en prime time, après le news ou devant le news. Donc j'avais une audience d'à peu près entre 50 et 70 millions de téléspectateurs. Alors, je mets le film là-dessus et ça éclate. Alors, on me dit que... je vous montre encore une fois l'os, ça d'une autre manière. Et ça, c'est le livre que celui qui a trouvé l'os a écrit. Le monsieur s'appelle Jean de Hanzelin de Bracourt. Mais le monsieur, il n'a jamais été apprécié, bien sûr, parce que son objet, on l'a caché. Il est mort entre-temps, bien sûr. D'abord, je vais vous laisser regarder ça, et puis je continue. On peut éteindre la lumière, s'il te plaît, parce que sinon, on ne voit rien. Le résultat de TV5, bon, je ne l'ai pas sur moi, mais c'est à peu près la même chose, si vous voulez. Mais à ce moment-là, le Premier ministre belge, à cette époque, qui était Guy Verhofstadt, peut-être vous vous en souvenez de lui, parce que c'est lui qui s'est excusé à propos du génocide rwandais. Et j'ai dû aller le voir, et il m'a dit, mais Georges, vous ridiculisez notre pays. Et moi j'ai répondu, monsieur le ministre, c'est l'inverse. C'est notre pays qui ridiculise le monde entier. J'avais raison, n'est-ce pas? Alors, par après, finalement, comme on se connaissait, il me dit, mais qu'est-ce que tu vas en faire? J'ai dit, monsieur le ministre, je ne suis pas mathématicien, je ne suis pas scientifique, mais je peux faire un film là-dessus. OK. Alors, on me donne un budget et je commence à mes recherches. Mais de plus que je entre dans l'administration pour avoir plus de précision, de plus que j'avais des ennemis. Et finalement, je rencontre le monsieur là qui était avec moi dans la pesanteur. Il me dit, Georges, je pense que tu n'organises pas bien les choses. Il ne faut pas mettre l'accent sur la colonisation. Il faut plutôt mettre un autre accent et de dire que les mathématiques, après 20 000 ans, appartiennent au monde entier. Et il me donne l'idée de mettre cette copie ici que vous avez vue en orbite autour de la Terre. Parce que lui, il a été désigné pour aller dans le laboratoire spatial, oui, Space ISS. Alors, OK, mais malheureusement, le monsieur qui était le responsable de vol parabolique pour tous les astronautes, parce que quand j'ai fait les vols paraboliques, j'étais avec des astronautes. Et on a trouvé une maladie sur sa colonne vertébrale et il ne pouvait pas aller dans l'espace. Or qu'il faisait ça presque chaque mois, si tu veux. Par après, j'ai découvert que c'était faux. On ne voulait pas qu'il parte avec l'os Ishango. Et puis, il a été remplacé par un autre monsieur, un autre astronaute belge qui s'appelle De Wine. Et lui n'a pas amené l'os Ishango, mais il a amené des dentelles de mouche. Voilà la différence. Alors, moi, comme je ne pouvais pas faire le film tel comme il était prévu, j'ai dû rendre tout l'argent que j'avais eu de l'État. Et je n'ai pas pu le faire. Mais aujourd'hui, je vais me venger. Je vais le faire à partir de l'Afrique. Je vais le faire avec des Africains et des amis, d'autres amis ailleurs. Mais surtout, ce qui m'encourage de continuer, parce que bon, je ne suis pas si jeune que ça, c'est que je vois que les enfants aiment les mathématiques. Je vois que les enfants aiment les sciences. Et je veux que notre jeunesse soit fière que c'est eux qui sont à l'origine des mathématiques mondiales. C'est eux à faire quelque chose avec les sciences et les mathématiques. C'est pour ça que je suis associé avec EMS. Et je pense que si nous allons arriver à là, et que surtout on se débarrasse de la colonisation qui est toujours dans notre tête, et qu'on sache très bien que la civilisation mondiale n'a pas monté le Nil, elle a descendu le Nil. Et la preuve, c'est l'os du Shango. On a toujours dit que les mathématiques étaient arabes. Faux. Et puis, on a dit aussi que par exemple, je vous donne un autre exemple, les pyramides. Nous connaissons les pyramides, hein, celles de Khéops, vous les connaissez tous. Mais il n'y a personne qui connaît les pyramides qui sont au Soudan et qui sont plus vieux que celles de Khéops. Donc, c'est-à-dire, toutes les connaissances que le monde entier détient, ils sont venus de chez vous. Ils ont redescendu le Nil vers l'Égypte. Hein? Parce qu'avec l'os du Shango, on a trouvé aussi des arpents, ensemble. Ces arpents, les mêmes arpents, exactement, on les a trouvés à Alexandrie. Mais Alexandrie n'a qu'à 10 000 ans ou 9 000 ans. Tu vois, il y a une grande différence de temps. Hein? Donc, c'est ça que je veux que les enfants, vous compreniez que vous aviez une fierté à l'intérieur qu'il faut exploiter. Je vous remercie.
Thank you very much. So we are going to go to our second talk or presentation by Professor Neil Geoffrey Turok. Professor Turok is the Higgs Chair of Theoretical Physics at the University of Edinburgh, UK, and an Emeritus Director of and Roger Penrose Distinguished Visiting Chair at the Perimeter Institute of Theoretical Physics, Canada. He is the founder and board chair of the African Institute of Mathematical Sciences, AIMS, and chair of the International Advisory Committee at the Higgs Center for Theoretical Physics. Turok earned his PhD in theoretical physics from Imperial College, London in 1983 and has held prestigious academic positions, including director of the Perimeter Institute from 2008 to 2019 and chair of mathematical physics at the University of Cambridge from 1996 to 2008. His career has spanned renowned institutions such as Princeton University, Fermilab, and Imperial College. Turok has received numerous honors, including the Officer of Order of Canada, the John Terence Tate Medal, and the James Clerk Maxwell Medal. His contributions to theoretical physics and science education has earned him honorary doctorates from universities worldwide. His leadership in scientific and educational initiatives, especially his work with AIMS, earned the Royal Academy of Belgium's Academy Prize in 2023. That is just a short bio, and introduce us to our second speaker, Mr. Turok, and the Professor of Theoretical Physics. Help me and join me to welcome him so that he can give us a talk.
It's lovely to see you here. Rwanda is a very special place right now. One sees a blossoming of activity and intellect and economic growth and so on, which is really encouraging. You are an example to the rest of Africa, and to the world. So in that spirit, I'm delighted to follow George and tell you where this magic has led us. And I hope I will just be confirming his story that what was discovered here at least 20,000 years ago truly is magic, and it indicates something about what we are as human beings. We have capacities which we do not understand, and they are leading us somewhere very interesting. So the origin of mathematics, astronomy, and design is, of course, here in Africa. This stone is 80,000 years old. I'm from South Africa, and so naturally I would try to compete with Congo and Rwanda. And my claim would be that geometry was invented in South Africa, at least. It's called the Blombos stone, and you see equilateral triangles drawn on its surface. So geometry and numbers in Central Africa. This is the world's first astronomical observatory in the south of Egypt. And of course, you're familiar with the pyramids in Egypt. There's evidence the first iron smelting, very high quality metal, was made in Tanzania. And of course, the first steam engine discovered was also developed in ancient Egypt, probably using ideas which came down the Nile. Here's the Ishango bone. Here's where it was found, not too far from here in Ishango. And what's the value of that discovery? Well, this is a huge underestimate of the value of mathematics. Mathematics is the underpinning, obviously, of information technology. The markings on the Ishango bone are the signifiers of numbers, and we now just process numbers. That's what information technology is, processing numbers. This is an estimate of the value, monetary value, of the worldwide information industry today, and it's growing fast, and AI is, of course, accelerating this growth. So put these numbers together, we get roughly $10 trillion today. That is one with 13 zeros after it. It's a lot of dollars per year. And I would claim that's the IP that came from Ishango bone. That's the intellectual property. So no wonder people are defensive. No wonder people want to hide it. It's extremely valuable. What's that? That's the past. Let's talk about the future. The future of science is Africa. Why? Many reasons, but one of which is that Africa is the youngest continent in the world. The median age in Africa is 19. So this audience may be typical of Africa, maybe a little bit older than average in Africa. Africa is the youngest continent, fastest growing population. Here I am in Scotland, Edinburgh. We're quite old. We're past it, frankly. We're over the hill. This is where up-and-coming youth are, and they are who drive science. So this is AIMS, and that's our new slogan. We used to have Einstein in our slogan. We changed it, and now our slogan is the following: in Africa's youth is the future of science. AIMS is many people all over Africa. We have 6 centers. We have 3,500 alumni now at master's level and PhD level. And I was very lucky to start AIMS, but let me emphasize, it's not just me. It's many, many people. I had a unique origin, much like George. I'm a Meti. My father's Jewish from Eastern Europe. They escaped from before the Holocaust in Europe. My mother's British colonial. And thanks to my history, I happen to know this man. You know who that is? Okay. The best leader of the 20th century, worldwide. I don't need to say his name. Do you know who that is? So he became a close friend of mine due to the fact we worked on the same field, which I'll tell you about. And I was lucky enough to introduce the two of them. They're very similar personalities, very warm, very funny, great sense of humor, and above all, incredible intellect. Here's the Ishango bone of physics. Okay? This is all known physics. This is how the world works. Okay? All the laws of physics are summarized here. Electromagnetism, nuclear forces, gravity. This is Einstein's theory of gravity. I'm not going to explain this formula. You have to study hard to understand this formula. But after you've studied for many years, you will realize this summarizes everything we know about physics. And it's all mathematical, but when you understand the mathematical logic, it becomes very simple. Strange, but very simple. For example, in the middle of the formula is this number I. Have you heard of I? The number I, is it bigger than 0? Is it smaller than 1? What is the number I? So if I tell you that the square of this number is -1, do you think I'm mad? If I multiply a negative number by itself, -1 by -1, what do I get? +1. So what number multiplied by itself is -1? I. Okay. So I was discovered in 1600s. It's another magic. And when you discover I, you can solve all the equations that you could not solve before. Infinite number of equations. And later on, 300 years later, I appeared in physics. And all the laws of physics. This is quantum. The fact that I appears in the middle of physics, and that's why quantum is so confusing. Okay, but mathematically, it's absolutely clear. So, simplicity. What we've learned about the laws of physics that govern the whole universe is that they are incredibly simple. It does take years to understand them, but when you have that understanding, it almost appears obvious. Okay, it has to be that way. This is the example, was mentioned Dr. Higgs. Dr. Higgs was a professor at my university in Edinburgh, Peter Higgs. He was the most shy person you could imagine. He's not loud like me. He's very soft, he's very quiet, and he hides away a lot of the time. And he wrote this paper. This is the complete paper. It's 1.5 pages. Okay? On this paper, about the Higgs mechanism, he won the Nobel Prize. Okay, it's easy to win a Nobel Prize. Right. Type this into ChatGPT. Type into ChatGPT, what is the origin of mass? Why do I have mass? Why can't I move at the speed of light? Because of this mechanism, okay? And he invented it in 1964, and he won the Nobel Prize 50 years later, half a century later. He's not a special person. Well, he is in some ways special, of course, but not that special. He saw something which eventually turned out to be true. And he saw it by thinking hard and processing all the information which was available to him. And it shows you something about the human mind. The human mind has the capacity to reach far beyond our everyday lives and see how nature works at a very deep level. Here he is. He's standing inside a tunnel at CERN, the largest experiment ever built on planet Earth. And he's pretending that he knows what's going on. I can assure you he does not. This was built by engineers, by experts, by construction people. He's a theorist. Okay, this is what a theorist does. Okay, and it's essentially mathematics, very clever mathematics, but it is extremely powerful. 50 years and 10 billion euros later is this huge laboratory, 27 kilometers around, where they smash particles into each other to see what's there, and they confirmed his particle was there, called the Higgs boson. Here he is, by the way, with this person who you should know. Do you know this person? He's Belgian. He came here. Ignace introduced him. I believe he was the first Nobel Prize winner to visit Rwanda. And he came here 2019, just before COVID. So he and Higgs jointly won the prize for this prediction. Now, this is my interest. That's the universe on very, very tiny scales. You see, the Large Hadron Collider at CERN is the most powerful microscope ever built. It can see distances smaller than 1/10,000th the size of a proton. Okay? A proton is the particle from which atomic nuclei are made. It's very tiny. You need a huge microscope to see very tiny things. Okay? On the other end of the spectrum, if you don't want to see tiny things, if you want to see very large things, you need telescopes, very powerful telescopes, and I'll show you a few. So the amazing discovery about the universe on the largest scales we can see is that it's incredibly simple. It's not complicated. The universe is not like a Lego construction that gets more and more complicated as you make more and more of it. No, it's not like that. The larger you go, the simpler it gets. The basic ingredients in our current model of the universe, which works very, very well, is we have radiation. Radiation came out of the Big Bang. It fills space. It's called the cosmic microwave background. It's radiation like in your microwave oven at home. Space is full of that stuff, and it came from the Big Bang. But don't worry, the temperature is only 3 degrees above absolute zero, not like in your microwave oven, okay? So we can survive, thankfully, because it has cooled since the Big Bang. In the universe, we have energy. We have a cosmological constant. I'll show you what that is. We have dark matter, which we are still learning about. We have atoms and electrons, like the stuff we are made of. And by the way, we are a minority in the universe. Yes. We are about 5% of the universe. The stuff like us is about 5%. The dark matter is about 25%. And I'll show you pictures of the dark matter. And the cosmological constant is most, about 70%. Then we have perturbations. These structures here that you see. So what is this picture? Here's the solar system. We have the Earth going around the sun. And then as we look outwards, we are also looking back in time. We're looking into our past, because the light travels at the speed of light to us. And so when we see objects further away, we are seeing them as they were longer ago. So this picture shows us our view of the universe, not only going out in space, but back in time. So here we are, we look outwards. We see this thing called the cosmic web. It's the structure from which galaxies and stars emerged. And before it, this red ring is the hot surface that emitted the microwave radiation, which now fills space. And beyond that is a blue circle. That's the Big Bang singularity. That is the place from which everything came, okay? And it's the most mysterious thing of all, and that's what I work on. I want to know exactly what happened at the Big Bang. Okay, there are some numbers characterizing this structure. There's an amplitude and a little tilt. These are technicalities. But just 5 numbers fit everything amazingly well. The universe is not complicated. It's simple. We don't yet know the full story, but it's telling us something very important. Just today, the Euclid satellite, you know, Euclid was the Greek mathematician who axiomatized mathematics. The satellite named for him is measuring the geometry of the whole universe. And here it is. There was a press conference at 1 p.m. today, and I encourage you to look online. I wasn't able to watch the press conference because I met George. That was more interesting. Okay. But there's some brand new results, and they're claiming new information about the dark matter and the dark energy. So we're learning a lot, and this is proceeding very rapidly. And you have a local expert in the physics department here. Remind me of your name. Joseph, who's an alumnus of Ames. And he will teach you more if you want to know. Here's the cosmological constant. This was a multi-billion-dollar experiment to see what is in empty space. I'm only joking. This was free. Okay? Because the cosmological constant, by definition, is completely uniform in space. It's completely constant in time. It doesn't evolve. It just is. Okay? It's the simplest kind of energy you can imagine. It has no structure. It doesn't change. And that's what Einstein invented in 1917 in his first model of the universe. He thought the universe would be 100% lambda. Actually, not 100%, a mixture of lambda and matter. He didn't get it quite right because he thought the universe was static, but in fact it's expanding. But nevertheless, like many other things, Einstein was more right than he knew. And it turns out that 70% of the universe, the energy in the universe, looks like this. No structure, okay? And there are a lot of observations now confirming that. How do we measure this? We measure this because it is repulsive. So we attract, objects like us attract under gravity. The Earth attracts us. That's why I'm standing here. That's why we could have the parabolic flight with 0 gravity. Okay? Cosmological constant is different. Its gravity is repulsive. It pushes the universe outwards and causes the universe to blow up. So here is I've called it lambda, the Greek letter. And here's a cartoon from Holland in 1930. Here is Professor de Sitter. He solved Einstein's equation with a cosmological constant. And here he is blowing up the universe. Okay, so this has been known for a long time, but only about less than 20 years ago, the first evidence came that the universe is full of this stuff. Here is Einstein, here is de Sitter. I wanted to show this slide because Einstein was an outsider. You see, just before Einstein, say 20, 30 years, 40 years before Einstein, Jews, he was Jewish, Jews were not allowed to go to university. Jews were money lenders or traders. They could not be engineers, mathematicians, scientists. Jews were excluded from European universities because it was thought they were inferior. Okay? And then Einstein and others came along and they said, we're going to prove you wrong. We are not only better than you, we're going to show we're better than you, and we're going to create new theories which will supersede yours. And so Einstein got his determination from his origins. And I want to encourage you to do the same. Right? Africans have largely been excluded from Western science, and you should take that as a motivation to show that you can do better. So here's dark matter. I don't want to take too long about this. This is the kind of measurement the Euclid satellite is making. Happy to answer questions, but in interest of time, I'll just go quickly. I'll mention, here are the large scale. So this is the sky that we see in this background radiation, the radiation coming from the early universe to us. It looks like this picture of the sky. This is the pattern. Naively, you say, just random. It's very far from random, okay? This plot of what we call the power spectrum, this is a mathematical notion. It basically tells you how strong are the fluctuations on a given scale on the sky. So again, I won't dwell on it, but this curve, the red curve, was predicted by physicists in early 1970s. And then finally it was observed in 2010 with high precision. And those 5 numbers I mentioned describing cosmology, those 5 numbers are used to fit this curve. I was very lucky in '94 to calculate what's called the polarization of this map. It's a property of the radiation. It can be polarized. That's why people wear polarized glasses, polarized sunglasses, right? So we calculated, what would I see on the sky with polarized glasses? Okay? And that's our prediction. And by the way, in this prediction, there are no free parameters. It's nothing to adjust. When you fix the parameters from this curve, you predict that one. And these are the error bars. The blue are the error bars. It's amazing. It fits beautifully. We understand the universe on the very largest scale. Why do we have this capacity? It's crazy. You know, it's crazy that we simple creatures who live on an ordinary planet going around an ordinary star can understand things so distant from us. I'm going to skip a few things. Black holes, we now see black holes. These are the first images of black holes. We see the origin of the elements. If you ask, where did gold come from? Gold came from here. There are these strange stars called neutron stars, which we observe in the sky. They are basically giant atomic nuclei, 3 kilometers across, an atomic nucleus. That's a neutron star. They orbit each other under gravity. I don't want to distract. These neutron stars orbit under gravity. As they are orbiting, they emit energy. You know, if I take a stick and I put it in the pond and I wave it round, waves will travel out on the water surface. So if you move heavy objects like stars around each other, they move around each other just under, they're attracted by gravity and they're orbiting each other like the sun going around the earth. They emit gravitational waves. And that's what causes them to lose energy, spiral inwards, collide. When they collide, it's like a huge nuclear fusion, and the nuclei fuse, the neutrons fuse the gravity, and their gravity, because they've collapsed, the gravity becomes so strong that light cannot escape. So we can't see inside a black hole. And now, these days, we are observing black holes all the time. They seem to be everywhere. And if you look at the Euclid announcement, you'll see more and more evidence for black holes. So if you ask, what is the most powerful microscope I could ever, in principle, build? It is set by the following. If the light I use in the microscope is short enough wavelength, right, so I shine light on the object and then the light is reflected off the object to me. When the light gets shorter wavelength, it becomes more and more energetic, right? X-rays are more energetic than light or radio. When they're energetic enough, you shine light on the object, you will make a little black hole because its gravity is so strong. Because the gravity of the light itself is so strong. When it hits the object, it will just collapse it into a black hole. So you can't make a microscope beyond that scale. It's called the Planck scale. So the smallest scale we believe we can ever see is set by gravity. Likewise, the universe is expanding very fast, dominated by this repulsive cosmological constant. And that sets a limit. Because if I consider some object further than a certain distance from us, it's traveling away from us so fast that any light it emits will never reach us. So there's a smallest possible scale and a largest possible scale, both set by gravity, and we live in the middle. Okay, so the smallest possible scale is called the Planck length. It's very tiny. An atomic nucleus is about 10 to the minus 16 meters, okay? But much smaller than that is the Planck length. Then on the large scale, we have the cosmic horizon, set by the cosmological constant. So these are two ultimate length scales. We live in the middle, life is in the middle. So it appears the universe is very simple on small scales, and very simple on large scales, and very complex in the middle. Okay, that's where we live. And we know that. Our society is nothing more complicated than human society. Okay, and physics has nothing to say about that. We can talk about this, we can talk about that. We have trouble with this one. Okay? And so that's where physics can understand, is the very large, the very small. And for those of you at school, I encourage you to learn about the geometric mean. If I give you two lengths, right, the biggest and the smallest, you can multiply them, but that's not a length, that's an area, right? If I take the square root, I get a length. And the length I get is about 30 microns, and that's the size of a living cell. So it's really true that life is right in the middle of the universe. And we don't understand even the origin of life. So I'm going to tell you a little bit about our theory, our new theory. Our approach is to find the minimal extension of known physics, which is consistent with all experiments and observations. And we believe the deepest paradoxes in those laws are our best clues. Now, you might say this is obvious. Why isn't everybody doing this? Okay? But if you read about physics on the web, you will learn about string theory and extra dimensions and the multiverse and all kinds of ideas. And I want to emphasize our approach is quite different. Now, I'm not saying we're right. We may well be wrong. But these topics are ripe for debate. And if you're a young African student right now, you should be thinking, do I want to get into this? Because maybe among you will be the next Einstein, the one to come along and show that Higgs and others, as brilliant as they were missing the main point. Okay? So let's talk about the Big Bang singularity. Here's our picture. Our new hypothesis is the universe is CPT symmetric. Now, I do apologize, this is technical, but I'm going to give you a picture of it. C is charge conjugation. You take matter and you make it into antimatter. P is inverting space. Take X and it goes to minus X. Okay? T is time reversal. The CPT is the most fundamental symmetry of the laws of physics which we know. And it is technical, but I'm going to give you a picture. We hypothesize the universe is CPT symmetric. We live on this side. Here's the Big Bang. Here's the universe coming out of the Big Bang. Starts with radiation and ends up with de Sitter, with the cosmological constant. What we noticed is there is a unique way to double the universe through the Big Bang. And technically, this is known as the method of images in physics. You know, if I have a mirror and I want to know what do I see in a mirror, there are two ways to solve the problem. Either I follow the light from my face to the mirror surface and I calculate how does it bounce off that surface back into my eye. That's one way to do it. There's another way, which is much more clever. You take yourself, let's say I'm right-handed, I make an image of myself, which is actually left-handed, and I put that image behind the mirror, an equal distance, okay, from the mirror. And then what do? I throw the mirror away, and I say, that's what I'll see. Okay? It's called the method of images. Well, it works for gravity. Our claim is that you can use the same method to understand the Big Bang, and in this picture, the Big Bang is a mirror. A mirror, it mirrors everything after the Big Bang. Okay? Now, there are two sides. Why are there two sides? It happens there are also two sides to every black hole. This has been known for 100 years. That if you look inside a black hole, mathematically, you will discover another exterior. We're on the exterior. We go into the black hole. There's another exterior on the other side. All gravitational solutions have this property. This is the analogy. So notice it has two sides. And time goes forward on this side and forward on this side. Right? There are galaxies forming this way. Okay? I've colored it green on this side because on this side it's antimatter. It's the opposite of what we are. Okay, but this is consistent with the laws of physics. The analogy, in physics, analogy works really well. Okay, nature is very economical with its principles. Once nature settles on one principle, it uses it again and again and again. So this is our hypothesis, that the Big Bang is analogous to the pair creation of particles in an electric field. This was understood in 1941. And let me describe how we understand the creation of an electron and its antiparticle, the positron, in an electric field. So I have empty space, no particles. I turn on an electric field, all right? When the electric field gets strong enough, it literally pulls a particle out of the vacuum. That's an electron. It pulls the electron out. But you must conserve charge. And so you pull electron out, it goes one way, and you pull an anti-electron the other way. That's called a positron. And so machines like CERN see this process, see these particles and antiparticles all the time. Now, the funny way of looking at this picture, which that gentleman Stuckelberg discovered, is that an antiparticle is a particle going backwards in time. Sounds strange, but that mathematical description is 100% accurate. Okay, so here is the particle, here's time and space. Imagine a particle that travels backwards in time, turns around, and goes forwards in time. That picture describes the production of pairs. You see, we only look at one particular time. So before this time, I see no particles. I come up here, something funny happens here, but beyond this point, I see one antiparticle and one particle. In our picture, this is the anti-universe, and that's the universe we live in. I'm going to try to explain the CPT theorem in 15 seconds. Okay? This is the most powerful symmetry known in physics. It's probably impossible to explain, but I'm going to try and do it in 15 seconds. Take this picture and say, what are the symmetries? What could I do with that picture? The simplest thing you could, it's a weird picture, right? Because the particle's going backwards in time and then going forwards in time. Well, let's rotate it by 180 degrees. Let's just turn it upside down. Why should nature care? So it turns out turning it upside down is PT, inverting space and inverting time. So let's turn it upside down. There it is, upside down. So we had a positron here. When I turned it upside down, I get an electron. Why an electron? Well, you see, it was going backwards in time. Now it's going forwards in time because I turned it upside down. So the interpretation is that it's an antiparticle, but it's the same thing. And this is the CPT theorem, that the laws of physics are invariant under this operation. Take the universe, the double universe, turn it upside down, it's the same thing. There's no difference between the two sides. From that side's perspective, we are the antimatter. From our perspective, they are the antimatter, but it's just perspective. Okay, to end, the universe is an amazing natural laboratory for fundamental physics. I won't go through this, but we live here in the late universe. We look back, it's a giant microscope. We literally can look back at the Big Bang. Here it is at the Planck time, where the visible universe at the Planck time was again about the size of a living cell across 10 microns. Okay? And we're lucky enough to see it. So thank you for listening.